Hi everyone, my name is Dego, and today I wanted to show you something about histograms. So how histograms work for images. So first of all, a histogram is a very simple tool that one can use. I have Matlab 2020 here, so I'm just going to quickly make histogram. So first of all, I'm going to make a vector of a bunch of numbers. Let's say, I don't know, 5, 7, 3, 5. Let's make a lot of these. And now, actually, let's get rid of the very large ones just because those are going to just mess up our histogram. Also, that wouldn't have worked. Okay, so we have this vector. Now we can actually make a histogram by doing histogram open bracket, and now we can put the actual data, so x, comma, and then I like to do one bin per value. So each value is going to have its own bin. Therefore, I'm going to do bin width, comma 1. And here we have a graph that shows from 2 to 3. So basically everything that is a 2 falls in this one. So we have this number here, we have this number here, and this number here. So we have 3 of 2. We have apparently 4 3s. So we have 1, 2, 3, 4, and then so on. So a histogram's quite simple. It just counts how many of each thing you have. It is very useful for statistics and so on. So I'm going to clear this. I'm actually going to delete x just in case I want to use that variable as well. And right now I have two different images, right? One of them, actually, they're both exported from Blender. It is a Blender benchmark file. I can show it to you, imshow. I have the image processing toolbox in Blender, so I can actually show you more easily with the imshow command the images. So let's do BMW 8-bit. And I'll tell you why it's 8-bit in a bit. Get it? Okay, so we have this image. So it's important to understand what this image is made out of. So first of all, let's look at, let's say, this value. So this value here, so this orange color here, this pixel that we highlighted is in, first of all, position 730 in the x direction and 380 in the y direction. It does start from the top left counting. So we start there. The R value, so this is an RGB image. It is a PNG actually. So it is not compressed at all. So it is 255, 143, and 126. So that means that the R value is complete, so it's full. The G value is about halfway, and the B value is pretty much exactly halfway. If we actually move this to be this kind of bluish lights here, we can see that, well, that's actually extremely white. Let's go to these. Oh, that's also, okay, let's go to this BMW sign here. We went on the blue area of this BMW sign, and we see that blue is complete. We see red is very low, and green is pretty much halfway. And we know that it is supposed to be blue. So that makes sense, right? So let's keep in mind that these values go up to 255. Now, let's do imshow of the 16-bit. And let's sort of click in the same area here. Now you see that these numbers, these RGB values, are much higher. So here you have pretty much the same ratio and proportions of the RGB values, but the numbers are just much larger. Now let's click on the orange here, or around here. So here we have the same ones as before as well, but again, these numbers are just multiplied by a factor of a lot. So why? Well, let's think about this. An 8-bit image is composed of 8-bit pixels. What this means is that each pixel has the ability of being from 0, or actually, yeah, it goes from 0 to 255. Why is that? Because we go from 0, which is basically the 2 to the power of 0 value, which is either a 1 or a 0, so it's on or off. So 2 to the power of 0 is 1, and that is either on or off. And it goes all the way up to 2 to the power of 8, and that is 256. Now we don't count the 256 because that would actually include the 8th power, and we actually go from 0 to 7. So that's why we do 0 to 255. So that is something to keep in mind. Now we saw that there were 3 different numbers. There was R, G, and B. And here we can actually see if we do size, and basically the image itself is composed of, first of all, actually let's just do size BMW 8-bit. So the image file is composed of what is essentially 3 different dimensions. So it's kind of like a matrix. So you can just imagine an image, but there are 3 different layers to it. There is the red layer being the first one, the G layer being the second one, and the B layer being the third one. And each layer has 1080 by 1920 pixels, because it is full HD. Now, we can actually plot or show only the specific color that we want. So we can do this, and a number. So what this means is that we can show all pixels in the vertical, all pixels in the horizontal, and only the first layer. And now you will see that everything will be according to the red image. And it is in grayscale because it is interpreting everything in that layer that is actually red to just be a number from 0 to 255. So, well, actually, let's not plot the 16-bit. Let's plot the 8-bit. And here we can actually see that the index is 255 here, but it is lower here at 46. And ignore those RGB values. That is just because the whole image is interpreted as grayscale, so it's actually assigning RGB values by itself, but ignore that. What we want is the index this time. So we have 46 as an index, and well, here we can see that everything is maxed out in the red. It's completely white, and as we can see down here, it's kind of lower because it is in the blue where it's supposed to be blue, in the BMW logo. Now let's let's keep this open. Let's just make it smaller. Let's do figure. We're just making a new window here. And let's do the same thing, but for blue. Oops, and blue is going to be the third. So now we have 2 images, but what is interesting is that they look quite different. So the figure 1, which is red, is actually much brighter where the image was actually let's also plot. Let's also plot the whole image. So we're going to do everything. And here we can see the original color image, and we have these other two. So we can see that the BMW is orange, therefore it's quite reddish. And we can see that the figure 1, which is the one on the right, it's supposed to be red, and we can see it is white where it is orange. Now we can also see that here where it is blue, it is basically black in the orange, but it is white in the blue. That makes sense, right? So now we can actually go into it and we can actually think about what this histogram should look like for every color. Well, let's start out with first showing what a histogram for the 8-bit looks like. So let's start out with red. Since red had a lot of white, then I would assume that there is going to be a lot of values in the 255 area. So let's actually have this figure here just to have it ready, just to remember what it looks like. And let's have imshow, or actually no, histogram. So the histogram command is very useful. I'm going to copy this and then comma bin width comma 1. And of course it replaced my imshow, so I have to do figure and then do imshow. So now we have this and this. So we can see that it spikes up in the low values here. So that is probably for the gray around here. So we can see this gray area is actually at 77. So that's around here. Then there's like, I don't know, darker colors. So up here it's 45. So it spikes around here at 45 or something like that. But then we don't have a lot of bright values until we reach 255. We can see 255 has 2,000 values here. Or no, actually not 2,000. It's 172,000 values. And that is because each pixel, so each pixel is actually one value. And that makes sense, right? Each pixel is one value in this histogram. So this histogram should actually have, let's do the math here, 1920 times 1080 should have this many pixels, so 2 million pixels. I'll exit off Steam so it doesn't bother me. So that is a lot of pixels, and what this means is that we actually have a histogram from 0 to 255 complete, and we can actually do the same thing but for blue. Let's do the same thing for blue. So it was 3, and the histogram looks a lot different. Let's also plot the blue one. I forgot, figure. There we go. So we have the histogram here, and we have the image. And the image over here, well, let's look at this. Well, the car itself now is actually darker, is actually in the 250 range, and well, it's at 27, 23, it's at 51, so it's a lot darker. So this area is a lot more basically populated, while the 255 area is a lot less populated. So, oops, what is the more populated? Why is it at 255? Well, the headlights are at 255. Probably the logo is at 255 as well. Probably this license plate, maybe 255. Maybe not even. It doesn't even reach it. So it's these values around here that are 255, the really bright colors. But this time it's not all of the car that is 255. So therefore this 255 value went down quite a bit. So that is a histogram for 8-bit. Now you sort of understand what a histogram for an image is. So now, what does a 16-bit image mean? Well, 16-bit means that you can actually go from 0, again, to 2 to the power of 16 rather than 2 to the power of 8. And this difference is actually, so you'd think, okay, if 2 to the power of, so if 8-bit, right, is, I don't know, 255, then probably 16-bit is probably like, I don't know, double that, so like 500 or something. Well, no, it is a huge difference. 8-bit, so 8 bits of information is 2 to the power of 8, so that's 256, but 16 bits of information takes it all the way up to 65536. So that is a huge difference. So actually, if we do 2 to the power of 16 divided by 2 to the power of 8, hopefully there's no issues with brackets here. Yeah, it's 256 times larger, which obviously makes sense because we're just subtracting the exponents when we divide. So this is a huge difference in scale. So therefore, with a 16-bit image, you can actually see a lot more detail in the brightnesses of each color. So we also have to remember we have R, G, and B colors for each pixel. So a 16-bit image is actually a lot heavier than an 8-bit image. Well, it's actually just double as heavy because if you think about it, each bit contains a specific amount of information. Obviously, it's just on or off, so it is binary, 1 or 0. Now, the amount of information you can actually hold in a 16-bit is this many possibilities. In an 8-bit, you have this many, 256. But the amount of the actual file size of the 16-bit image is just 16 bits, so 2 bytes rather than 1 byte. Therefore, you're actually just doubling your file size. Obviously, if you just have one color, if you have multiple colors, then that would be doubled in each one, but it would still be doubled. So you can have, let's say, a 8 megabyte image would turn into a 16 megabyte image. And actually, you can actually do this math. You can say 1080 times 1920. So that is the actual size of the image. And I'm doing 1080 for, usually you do 1920 by 1080. But since Matlab reads vertically first and then horizontally, I'm just sticking to that convention. So you have 1080 by 1920 times 3, because there are 3 colors, times, well, it's 8 bits, right? But each bit is a byte, so we're divided by 8. So here we have, actually, each file is actually 6.22 megabytes for 8-bit. Now, if we were to do 16-bit, each file is 12.44 megabytes. So it's exactly double. But the thing is, you're actually holding a lot more information in there. So if you think about it, you're actually holding a lot more information than the file size leads you to believe. You're just like, okay, it went double in size, but that doubling in size means that you have a lot more information because each pixel contains 256 times the amount of data or information, not actual data. It just contains twice the data. So hopefully that makes sense. So now let's actually look at a histogram for 16-bit. And it will not actually look as pretty as the 8-bit histogram, just because everything is going to be so small. And I'll show you what I mean by that. So let's start out with this, the first one, and the red. And let's actually have the car as well show up. So 16, and let's show the car. So let's do, what was it? 1. So we have the car. And again, this is 16-bit. We can see that because we are at an index of 65540. And I'm pretty sure it's rounding because it should be 65536, and there's no way it actually gets to 40. So it is rounding, funnily enough. So red, here we go. Red is saturating, and by saturating I mean it is actually getting to the highest value of the bits it can. But here you can see the histogram. It's much flatter. What does that mean? What is this? Well, and you see a huge spike here. What does this mean? So actually, this spike at 255 dot, 1 sec. This should actually, I'm just zooming in and out here. The spike should actually be at 1 bin width. So this spike is at 255. Oh, why is it 30? Anyway, so this spike actually has the same amount of white, or like complete white, with respect to red, so complete red it would be, as the 8-bit image. And why is that? Because the same pixels are actually saturating. So with 16-bit, you're still going to have pixels saturate. It can still happen. And what that means is that the same pixels might actually get to the very highest values that you can see. The only difference is that the dynamic range, and this is a very interesting concept, the dynamic range goes up. So the very details in color difference you can see will be shown. Obviously, you can't actually see that with a monitor. Usually most monitors, if they're 8-bit monitors, they're going to show 8-bit color. That means it's only going to show the 256 combinations. But if you have, for example, I have a 10-bit monitor. I'm not using the 10-bit functionality here, but I should be able to see more color combinations than an 8-bit monitor. But at the same time, I'm not going to be able to see 16-bit. That is a lot. So, and just for an idea, when you enable, let's say, 10-bit color in a game, you can actually see 2 to the power of 10 colors, which is 1024 colors rather than 256. And you can actually do this if you go to control panel, if you have an NVIDIA card, and hopefully it opens up quickly. Here we can see that if we go to change resolution, we can see here output color depth. I'm at 10-bit, but my monitor isn't actually enabled. But there's 8-bit per color that you can have. So this is how you would enable it if you have a monitor that supports it. And then you can actually play some games in 10-bit, or you can even maybe do some work on that monitor, maybe some creative work with different programs with that 10-bit functionality, which the colors look amazing with 10-bit. You can actually see a much larger range of colors, which means that things that are maybe sort of all black in a game, if you're like into shadow, if it was all black in 8-bit, in 10-bit you could actually see differences, and you can actually see things in shadow. If your screen is like half shadow, half light, in the shadow you should be able to see things, which is really cool. It's really hard to describe the difference, but it's once you see it, it's a very different, interesting thing. So I was showing you this. So we actually have the brightest values, but then we have a lot less spiking going on here. Why is that? Well, in 16-bit, we actually have, like, what I mean by spiking is we don't have the high values here that we had before. We actually had, well, I'm going to open up here, figure, and I'm going to open up the histogram for 8-bit. And here we can see that 8-bit, actually the same color, same thing, actually got to this, to 10. So and this would be actually 100,000, I'm pretty sure. Yeah, 100,000, right? But here we see that that's not the case. It's much lower, right? And why is that? Well, we got to remember that each one of these bins actually comprises one value. So each value, so 250, so 46 to 47, for example, here, actually translates to a completely different thing in here. So if we actually zoom in here, and you'll see some interesting phenomena here. Oh, of course, I can't move like that. So here, look at that. So each one of these values, 11, so this is rounding a lot, but it shouldn't be. So this is actually supposed to be one bin per cell, but you can actually see, or 1 bit per bin. So you can see that there's actually 10 here. It's just not, it's rounding it in the display. I can actually change that, but it's too much work. So basically, you can see that each one of these bins is actually filled with many of these other bins. So what would be in 255 or 256 available values, this value that gets up to here is actually a combination of many of these values, many of these values being basically bunched together. But because they're not being bunched together in this graph, they're actually separated. It actually shows as much less, so a fraction of what this histogram says. So that's a very interesting concept. Another interesting thing is that a proper histogram should actually not look like this. So because I exported it from Blender, I'm not really sure how it exports, and maybe the actual image wasn't meant to export at 16-bit. The colors weren't 16-bit, so that means that there are a lot of bins here that are not being fully used. So here they're actually being used a little bit, but this should actually be a continuum. It shouldn't go down like this. And you can see it's a repeated pattern. So there is a systematic problem with this sort of exporting, the 16-bit exporting in Blender. Now, I'm going to let that be, but basically, just so you get the idea, we have much less of each value because each value is now at a higher resolution. So imagine each bin, actually, just imagine making these bins larger. So if I were to do histogram of the 16-bit again, but if I were to make the bin widths 255 or 256, let's say, look at this. Now it actually does look like, now it actually does look like the 256. So actually I'm going to close everything so we don't confuse it with the other one. Oh, actually, that was it. So this is the 255. So this actually looks exactly like the 8-bit. And the reason for that is that we actually have we're basically binning it in the same way. So a lot of these programs, what they might do, probably not what they actually do, but what they might do is start off with a 16-bit image, and then if you want to just grab an 8-bit image from them, you would do something like this. You would just basically bit shift everything. And what is bit shifting? I can actually just keep going with this, but I'm going to stop at bit shifting here. So bit shifting is actually moving. So let's say a number has a, let's say it's this. I'm not sure if this is 16 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And let's add a 0 here, 16. So we have 16 in here. 16 values. Not sure if this is large enough for you to see. Let's increase the font here. No. There we go. So this number here, we actually want to bit shift it. And if you bit shift it, or just concatenate it, or not concatenate it, you would cut it. You would be basically taking the most important bits, so the most significant bits is the actual terminology, the 8 most significant ones, and you would get rid of the least significant ones, right? So now, if you were to do that, this number, let's say this number, actually, let's actually translate. Oh, I got rid of it. So if I were to do decimal, is it dec to bin? Bin to dec. Perfect. So let's say we have this number. We have 10001, and let's actually count this. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And I think I got to 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, 16. Perfect. So we have this number. This number is this in 16-bit. If we were to bit shift it, so get rid of the bottom 8 to actually just leave the top 8, so we're getting rid of 1, 2, 3, 4, 5, 6, 7, 8. We're basically rounding it. Oops. And that is because we're actually getting rid of a lot of these values. But basically, by doing this and putting it in the 8-bit space, obviously 8-bit can't get to as high as a number as we want it. But because these numbers are normalized, again, this is a lot to understand, but the 16-bit number that we get in this car image is actually normalized. So it brings it down basically to 8-bit so we can see it with our monitor. So basically what it is doing is it's just making the image visible. Therefore, it is bit shifting it down. Therefore, it is rounding to 185, let's say, from this number. Now, the thing is, what is actually happening is that it's rounding to the nearest, basically 2 to the 8 in this 16-bit. So it's just like if you were to do, if you were to have like this number in the decimal system and you wanted to round to the nearest hundredth, you would do this. So 8-bit and 16-bit, it's just as if you had a, let's say, a number in the 100,000. So let's say 1, 2, 3, 4, 5, 6, and you were to round it in the basically realm of decimal. So if you were to round it, it would actually look like this. Now, if it was converted to the just 3 bits, it would look like this. So because binary isn't as nice with our numbering system, it actually looks like this, not this rounding, but it is basically just like decimal rounding. So that's hopefully makes it a little bit easier and gives you a little bit of interest into looking more into what bit depths mean in an image, and how basically each image is composed. Again, these images that I imported are not at all compressed. That means that we can actually see the color, each pixel accurately, and it's not going to be like changed in any way. These are the actual pixels of the render. The only issue is that the 16-bit was actually not properly done in Blender for some reason, maybe my settings or something, but it gives you a general idea of what 16-bit is compared to 8-bit. So if you have any questions, you can comment. I know I don't get a lot of views on these, but if I can help anyone, that's great. I can definitely answer your questions. Thanks for watching, and hopefully I can make more of these if I come up with any ideas of what to cover. Goodbye.